Sahik will continue his lectures on lattices. Good.
So, existence. So, which group admits lattice? So not every group admits lattice. For instance, we saw that if a group has a lattice, then it's unimodular, and there are many non-unimodular groups. But there are also many unimodular groups, like nilpotent group doesn't have to admit lattices. There is a beautiful theory of Malchev, elementary but very beautiful, and in particular it says that an nilpotent Lie group admits a lattice if and only if it has a rational structure. So it's you find a base such the coefficient of that defines the Lie product are rational, and actually you can see the rigidity and arithmeticity in nilpotent group if you. So every lattice there is nilpotent. So and there are nilpotent group which doesn't have rational structure, so they don't have lattices. There are also a simple group, locally compact simple group with no lattices. So example was constructed by Shachar, Uri, Pierre-Emmanuel, and myself. But classical theorem of Borel says that for simple Lie group or semi-simple has many lattices always, uniform lattices and non-uniform lattices. So the theory is non-empty. These are the most interesting objects, and in fact there is a okay, let me talk about arithmeticity.
Lattice is a discrete and confinite volume?
Yes, a discrete subgroup of with a finite volume fundamental domain. So yesterday I mentioned a Ziegel theorem that SLN Z is a lattice in SLN R, and this evolved to a very general theorem of Borel and Harishandra, which says that if G, let's say so, let G be a Q group, so it's algebraic group defined over Q, and which has no Q characters. So in particular, if it's a semi-simple group or a perfect group, so it doesn't have characters at all, but even you may allow characters, like in the nilpotent case, but not, okay, sorry. So, okay, so it doesn't have character which are defined by polynomial over Q, then G of Z is a lattice in G of R. And the theorem also say when this lattice is co-compact. So it's co-compact if and only if G doesn't have co-character, so it doesn't have one parameter there is no morphism from Gm to G, which is defined over Q. So okay, so that's a source of most lattices. Let's write GZ inside G is a arithmetic lattice. There is something that almost any of the lecture did and I didn't, which is a restriction of scalars. So let me repeat it. So let fx y z be the following form. So x squared plus y squared minus square root of 2 z squared. And then define G to be the group that preserve this form. So it's a group which is defined over the number field q square root of 2. And and define gamma to be G of the ring of integer z square root of 2. And so restriction of scalars that Gil described yesterday from q to q square root of 2 of g give you the group G cross G sigma, where sigma is the Galois conjugate, and this, if you look at it over R, you get SO3, SO21 cross SO3. And what Gil said, so if you denote this group by H, so it turns out that H of Z, if you define the restriction of scalars properly, it is isomorphic to G of the ring of integer you started with. So we get that this group, so by the Borel-Chandra theorem, this group is a lattice in H. So this group is a lattice in H by the Borel-Chandra theorem, but also by what Nicola showed explicitly yesterday. So it's a co-compact lattice in this group. So if we call it gamma, so gamma is a lattice in SO21 cross SO3. But this is compact group, so we can project it to a lattice in SO21, which is basically isogenous to SL2C, which is a group of isometries of the three-dimensional hyperbolic space. SL2R, yes, right. Two-dimensional hyperbolic space. So you start with the abstract group. You do this and you realize that it's a fundamental group of a compact surface, hyperbolic surface. So in particular, you know it's a one-relator group. You have a presentation of it. So this up to finite index, because this group will have torsion, but a finite index subgroup is a surface group. But why did I do that? I wanted to recall you that to be more in the general situation, we have to divide by some compact factor. So this is the definition of an arithmetic group. So let G be, say, a simple, or let G be a Lie group. Lie group. Okay, let's say semi-simple. And gamma in G a subgroup. Gamma is arithmetic if there is a Q algebraic group a surjective map from H, which is the real point, onto G with compact kernel. So this is the compact kernel here, such that gamma is commensurable to the image of H of Z. And recall that two groups are commensurable, meaning that the intersection is finite index in both. And the Borel-Chandra theorem says that the arithmetic group is a lattice. And basically Nicola proved it in the case of SOPQ. And what I would like to explain is so this is one of the highlights of this theory, but the converse is also true in a, not always, but in a quite big generality. So this is Margulis. Margulis' theorem says that in many cases also the opposite is true, that every lattice is arithmetic. So hopefully this is what I will reach in the end of this talk. So, but in these groups, in SL2, we know that actually there are only countably many arithmetic lattices, but continuously many non-arithmetic lattices. In SON1, also there are most lattices are non-arithmetic, as Vikram will show in his talk. But in high rank group, so in SOPQ, where both P and Q are at least 2, or in SLN, where N is at least 3, all lattices are arithmetic. This will be somehow what I aim to show. But this is a consequence of rigidity. So let me discuss a bit rigidity. Yes, so if you have a group G and you have gamma and delta are both subgroup, then gamma and delta are commensurable if the intersection gamma and delta is a finite index in each of them. So, but if one of them is a lattice, it's enough to check that it's a finite index in one of them, and it's also a lattice, and then it's finite index in the second one. So rigidity. So there are many rigidity theorems. I will mention 3. Maybe the most classical one. Let's start with local rigidity. So by the way, lattices, so this is another theorem, that lattices are finitely generated. What?
I mean, even though it's the ambient group is compactly
No,
generated.
no, it's not true even. No, there are compactly generated groups such as lattices. Oh, okay, we speak about, okay, lattices in Lie groups. Yes, connected Lie groups. To be more precise, if D of gamma is the minimal number of generator, then you can show that D of gamma is bounded by a constant times the volume of G mod gamma in semi-simple Lie groups. It's true in greater generality that if G is a compactly generated locally compact group, then any co-compact lattice is finitely generated. This is easy. It's not true that every non-uniform lattice is.
C is a function of the group of G?
C is some constant depending on G. On the you can normalize the Haar measure such that it's 1. But so anyhow, this is a remark. But lattices are finitely generated. So let's forget that the group is a lattice. For a moment, let gamma be a finitely generated group. So gamma is a group generated by S, where S is a finite set.
Gamma is torsion, this is
Yeah, this is known in general. And they are also finitely presented. But
the bound.
this bound is true in general. You don't even with torsion. So okay. Yeah, this is actually, it's a theorem, so it was proved case by case for higher rank Lie group. it was the motivation for Kashdan to prove property T. He deduced that lattices are finitely generated by property T. In rank 1, it was proved by Garland and Raghunathan. Later, Gromov showed a geometric proof for torsion-free lattices. And using his idea, I proved this, but also for torsion. So, so we consider now a general finitely generated group, and you consider the representation variety. All the homomorphisms from gamma to G. Okay? So this, you can think of it as a subspace of, in a non-canonical way, of G to the S.
The number C depends on G, yes?
The number C depends on G, but yeah, I just wanted to remark this. I have a lot of plans for this talk, so yeah, this is. I just want to say that this is a finitely generated group, and we can consider the space of all representation of gamma into G. So you see, in a non-canonical way, you can see it as actually as a variety. So it's so this sits inside G to the power S. What?
This is a theorem that is finitely generated. This is what's called local rigidity.
No. This is just a theorem. I didn't say what is local rigidity yet. So I look at the representation variety. So this is if you want, this is an algebraic variety. If gamma is a group generated by S and some set of relation, so you see that this is an algebraic variety which is defined by these relations.
If G is algebraic.
G is an algebraic group. So, and the variety of representation is algebraic variety, is a fine algebraic variety. And you see that if G is defined over Q, then also this variety is defined over Q. And there is also a natural topology here because G is also has a Hausdorff topology, so it's induce a Hausdorff topology on this space. And gamma is called locally rigid, or F from gamma to G is locally rigid if let me say that gamma inside G is locally rigid if the inclusion has a neighborhood consisting of conjugate. So one way to get a different representation is by conjugating the inclusion by some elements close to the identity, and gamma is called locally rigid if any deformation which is sufficiently close to the inclusion is of that form.
So neighborhood is in the Zariski topology?
Neighborhood in the Hausdorff topology. In the, yeah. So then this is the definition of locally rigid. And we know that lattices in SL2R are not locally rigid. This is, you can see it from Teichmüller theory. You can deform the hyperbolic structure in many ways. But the theorem from the early 60s of Selberg, Calabi, and Weil, so he 60, 61, 62, but he did it, it's called Weil local rigidity theorem, says that, no, but, okay, for a reason, Weil proved the general case, but let me say it, so if G is simple, Lie group not locally isometric to PSL2R, then any uniform lattice is locally rigid. So this is Selberg. Selberg proved it for SLN with n greater equal 3. Calabi proved it for SON1, I think, or SUN1, I don't remember. And Weil did the general case. So it's called Weil local rigidity. And so this is quite good theorem, so I would like to explain why.
I is the diagonal, right?
Sorry? I is the inclusion. I is the, so gamma is a subgroup of G. So I think of I as a map from.
But you look at it in the permutation variety.
Yes, I is a point. If gamma is a subgroup of G, then I is a point in home gamma G, and it's the inclusion. So any homomorphism, if you deform slightly gamma, so what does it mean to deform? You move a bit the generators, but you want any relation to be satisfied. Then you want it, okay, to be a conjugation. So that's a.
Why uniform? Is that somehow
So.
what they were able to prove, or that?
Good question, and the answer that you don't need it, but it's much harder. I mean, you need. Okay, not completely true. So, what Margulis proved, the general theorem, which include this name plus Margulis. No, not just Margulis, also Garland, Raghunathan. Okay, I will not say all the names. If G is neither SL2R and not SL2C as well, then all lattices are locally rigid. So it follows from superrigidity in higher rank and by the work of Garland, Raghunathan in rank 1. In SL2C, non-uniform lattices are not locally rigid, but uniform lattices are, and in SL2R, even uniform lattices are not. Let me give you. So today I will not give proofs of rigidity theorem. Tomorrow I will do something. Today I will try to explain application of the rigidity theorems. So local rigidity has very nice applications, and let me show one. So here is a lemma. Actually, I will show two. So here is a lemma. So in algebraic geometry, if X is an affine variety defined over Q, then X Q bar is dense in the Hausdorff topology in X R, where Q bar is the algebraic closure of the algebraic closure of Q in R. And this lemma is not very hard. It's basically a consequence of the implicit function theorem, but it's very, very useful. So basically, you have a point. You have algebraic variety. You have a point in the a real rational point, and you want to deform it to a rational point. So some of the variable you can deform freely, and the rest are determined by the implicit function theorem as algebraic points. This is not a proof, but this is the moral idea of the proof.
So Q bar for you is not a direct closure of Q.
Q bar is Q bar intersection with R. Let's call it Q tilde. Q tilde is Q bar intersection with R. And so let's apply this lemma and local rigidity and see what's happened. So let gamma be inside, let's say, G let's say it's SLN R. N is at least 3. A uniform lattice.
It doesn't have to be smooth.
What?
It doesn't have to be smooth.
Maybe it has to be smooth. I don't. Maybe not. Let's check it later. So I wrote a proof of it. So we can look at the. Yeah, it was a while ago. So so let gamma be a uniform lattice in SLN R, and then I look at home gamma G. So this I call it X is a algebraic variety defined over Q. So next to the inclusion there is a algebraic point. By local rigidity, this algebraic point is conjugate to gamma. So it implies that one can conjugate gamma into SLN of the algebraic closure. What? The algebraic closure of Q inside R.
Can you repeat the argument?
So I take I. By this lemma next to I have a algebraic point. Algebraic point means a representation such that all the generators are sent to matrices with algebraic coefficient. By local rigidity, it's a conjugation of the inclusion. So in particular, a consequence of this is that any eigenvalue of a matrix in a lattice is an algebraic number.
Right, where did you use co-compact?
For local rigidity.
But you said it's true also in general.
It's true also in general. Here I don't use co-compact. I don't need co-compact. But Selberg, okay, this appeared in Selberg's beautiful paper from 1960. And I think this was one of the motivation of him to conjecture. So it actually means that this sits inside K, where K is a number field. Because gamma is finitely generated, so you need a finitely generated algebraic extension. It's a finite extension of Q. And maybe that was the motivation of Selberg to conjecture that any lattice is arithmetic. But the way he conjectured it was not correct, and it was corrected by Piatetsky-Shapiro, who added this factor that before moving on, by the way, Pierre-Emmanuel discussed lattices in the non-classical situation, in locally compact groups, and he mentioned today that most of rigidity does not hold. So this group which we think about, the semi-simple Lie group, are the isometry group of Riemannian locally symmetric spaces. And similarly, you can consider a isometric group of more general spaces. So so let me just write an extension of this local rigidity. So it's a theorem that Ariel Levitt and myself recently proved. We show you that H2 is the most interesting case. So let X be a cut zero space, irreducible cut zero space. So you cannot write it as a direct product. I'm not going to define, but it's a generalization of I will tell you later. It's a generalization of non-positive curvature. It's a geodesic metric space such that if you draw a triangle, the distance from this point to that point is not greater than the distance if you draw the triangle on the Euclidean space. So it's a
It's zero curvature. So it's like
zero curvature. It's good. Zero or negative. So non-positive curvature. So generalization of non-positive curvature. A cut zero irreducible, and suppose that X is neither R, neither hyperbolic plane, and also suppose that G is the isometric group of X, acts co-compactly on X. In the classical case, it acts transitively, but in general, then all uniform lattices are locally rigid. So you don't have most of rigidity, but which I will say uniform. All uniform lattices are locally rigid. How is time?
You assume X is
Half. This is half of the. What?
should X be
Yeah, proper. Let X be an irreducible proper. So balls are compact.
what? So what about the plane? It's irreducible.
Irreducible and not Euclidean. So you can you don't need to. Okay, you can write more general version, but you don't want Euclidean factors, and you may allow hyperbolic two-dimensional factors, but then you need to restrict to irreducible lattices. Anyhow, this relies on the theory developed by Monod and Capras of groups acting on cut zero spaces, which we dedicated one of the recent Deboker conferences to study that. Anyhow, I said more. I said that not just uniform, but all lattices are locally rigid, and this implies something. This implies another beautiful consequence, which is called Wang finiteness theorem. These are the two, my favorite two applications of local rigidity is this algebraic thing and the Wang finiteness theorem, which says the following. So again, we assume that G is not SL2R and not SL2C, but it is a simple Lie group. Then for every V, there are only finitely many lattices in G of co-volume bounded by V up to conjugation. And why is that? So it's so one gave a compactness argument here, which relied on the Kazhdan-Margulis theorem, which I mentioned a version of it yesterday, and I will prove it in a later talk. So let me recall Kazhdan-Margulis theorem. There is an open neighborhood. So let's decide. Let G be a simple Lie group, non-compact. I mentioned that lattices has unipotent elements. They proved it in the same paper that they show there is an identity neighborhood U such that any lattice gamma in G admits a conjugate which intersect G gamma such that this intersection is trivial. So in particular, there is a lower bound of the co-volume of lattices, but more than that, you can conjugate such that the intersection with a given U, which is independent of gamma, is trivial. So then we go back to the compactness criterion that Nicola mentioned in his first talk. He mentioned it as a Mahler criterion, you call it? So Mahler, for lattices in Rn, it's called Mahler criterion. For lattices in general groups, it's called Chabati-Mahler. So the compactness criterion. So if you look at all lattices, the set of lattices gamma in G such that the volume of G mod gamma, let me write it like that. The set of all gamma in G such that the volume of G mod gamma is less than a given number and gamma intersect U trivially is compact. So this is a compact in the right topology. And the right topology is non-explicitly Nicola defined it. It's called the Chabati topology. The topology of closed subgroup. So a sequence of subgroups converge to a group if any point in the limit is a limit of. So who never heard about Chabati topology?
I never heard.
What? Okay. Let's say that gamma n converge to gamma if every gamma in gamma is a limit of gamma n in gamma n, and every limit is in gamma. So every limit of a subsequence is in gamma. So this is a natural topology on closed subgroups, and you see that if you look only on subgroup that intersect U trivially, then the limit will also intersect U trivially, or maybe a slightly smaller set trivially. No, if U is open. So okay, and so it will still be discrete, and this condition also goes to the limit. The co-volume of lattice in the limit is also can only reduce. Cannot be larger. So a limit is again a lattice. So this is a compact set. And
This topology, the discrete groups are not closed. So this is why you choose this thing.
Discrete group can converge. So yeah, if you homothety of Z can converge to R. But yes, but this is a compact set. And local rigidity tells you that the conjugacy classes are open there. So it's an open cover, so it's only finitely many. But I cheat you, because local rigidity is with respect to a different topology. It's the topology of the deformation, which is not exactly this topology. But there is a small two-line argument to pass from one topology to another. So this is basically the proof that there are only finitely many. Is it more or less okay, or? So, what? Up to?
Yeah, up to what you're not telling us.
Okay, I can tell you that, but okay, in the you can ask it in the questions time. So no, and so the first application that lattices has some at least arithmetic algebraic eigenvalue has no generalization to general locally compact group. But this finiteness theorem you can prove analog result for general cut zero spaces. Okay, the next really maybe the most beautiful rigidity theorem is most of rigidity. It does not imply and it does not the music somehow disturbed me. So is there maybe you can put air conditioning. So most of rigidity does not imply local rigidity and but it's much stronger when it holds. So again, let G be a simple Lie group, and we assume again that G is not SL2R, not locally isometric to SL2R. Gamma in G a lattice. Actually, let's say you have two lattices, gamma 1 and gamma 2 are lattices, and gamma 1 is isomorphic to gamma 2 if and only if, gamma 1 is isomorphic to gamma 2 if and only if there is an automorphism of G, which is basically an inner such that sigma of gamma 1 equals to gamma 2. Almost all, up to finite index, all automorphism of G are inner. So basically it says that gamma 1 and gamma 2 are conjugate. So two lattices which are, if they are isomorphic as abstract group, they are conjugate. So this is I think at the time, much more than people expected. It's much stronger than the Borel conjecture in this situation. It applies in SL2C also for lattices which are not locally rigid, for the non-uniform lattices. So this is it has infinitely many applications. I don't think I need to demonstrate why it's important. It speaks for itself.
So what is the relation between this and rigidity? No one implies no one?
Directly no, but with some additional work you can use most rigidity to prove local rigidity if you know more things.
But like, they don't hold for any group, yes, so the generality, one generality is including the other generality?
No, so okay, Pierre-Emmanuel showed this morning that the group of the product of 2, 3, you don't have most rigidity, but I just told you that you have local rigidity there. On the other hand, for non-uniform lattices in SL2C, you don't have local rigidity, but you do have most rigidity. So yeah.
There is a relation, but not.
Yes, but the conclusion of this is much stronger. It's not just the formation which is close to the identity comes from conjugation, but I mean, a priori you don't assume here that these two lattices have the same covolume. It's just isomorphic as abstract group. So this is local rigidity. This is most rigidity. And now I will formulate superrigidity. So it is much stronger result than most rigidity, but it also assumes more. So let's say let G be a simple again. There is always version for semi-simple. Simple Lie group of real rank at least 2. So for example, SLN R where n is at least 3, or SOPQ that Nicola discussed, where the minimum between P and Q is at least 2. Let H be an algebraic group a simple algebraic group and let's say it's simple, not almost simple, so center-free, simple center-free algebraic group, and in fact, you don't need to assume simple. You can assume much less. Okay, let K be a local field. So it could be R, C, QP, finite extension of QP, and let F from, okay, let gamma be okay. Gamma is a lattice in G, and let rho from gamma to H, which is the K rational point of H, be a representation with unbounded, with, let's say, Zariski dense unbounded image. Then F extends.
F is rho.
What?
F is rho.
And then rho extends to G, to a map to rho tilde from G to H. Yes? So you have a representation from gamma, from the lattice, to some simple center-free algebraic group over a local field, which could. No, but okay, let's assume. No, you don't know, but but it will follow. So let gamma from H to H be a representation with Zariski dense unbounded. So this is for the Zariski topology, this is for the local field topology image. Then rho extend uniquely to rho tilde from G to H. So yes, so this is a so Nir proved this theorem for the specific case where gamma is SL3Z.
But then from a subgroup.
What?
But then from a subgroup, no?
Yes, but you can. Okay, the assumption was a bit different, but the conclusion a bit different, but it's equivalent to this. You can show it's equivalent to this, but the strength of this theorem is that it does not. It's not just for SL3Z; it's for any lattice in SL3R. So this theorem has many applications. For instance, as Nir said, once we know that every homomorphism of SL3Z extends to SL3R, then we have the theory of representation of SL3R. It's a Lie group, maximal weight. We know all the representation of this group, but there is actually even a nicer application of this result, and this is the arithmeticity theorem that I mentioned before. So one of the nicest application of this theorem is the arithmeticity theorem. Corollary: every lattice in G is arithmetic.
So if the field is QP, then
The conclusion is that such a thing doesn't exist.
Yes. So you have a map. You have a map from SL3Z to SL3QP, but the image is in SL3ZP. It's bounded. So you don't have a map which is unbounded. And the fact that the image is Zariski dense in a simple group is you can assume less. All you really want is that the center of the Zariski closure is trivial.
You thought there was something very similar, but there was also a finite index subgroup.
This finite index subgroup is because I said the assumptions are a bit different. So here I assume that the image is unbounded. So what can suppose you apply this theorem for SL3Z. So we have a representation of SL3Z into GLNR. What can happen? One thing that can happen is that it's actually a representation of SL3R. And the other thing that can happen is that the image is finite. And that's the only two.
And you can take some kind of product of.
Yeah, and I mean, okay, you can involve, so the product, but then the image will not be let's say, connected, Zariski connected. So for SL3Z, it's an exercise that this is equivalent to what Neil said, but this is much. So I want to sketch. I want to sketch this corollary. This is I think such an amazing consequence, such an amazing fact that Selberg conjecture is actually true. That every lattice is in higher rank group is arithmetic. So here is how much time I have?
7 minutes.
7 minutes. It's enough. Sketched.
The rigidity follows from this rigidity?
No. So yeah, local rigidity follows from superrigidity, but as I said, local rigidity is true in greater generality. But when you have superrigidity, you can deduce local rigidity. Most rigidity also follow from superrigidity when you have. Yes, most rigidity also follow, but again, most rigidity also. For some people don't care about high rank group; they care only on SL2C. People study hyperbolic manifolds. For them, most rigidity is more valuable. For us, this theorem is much stronger and.
I look about this not as a theorem but as a property, and then I ask like.
Yes.
Generality of the
Yes.
property.
This is stronger. This is
Stronger property.
super is stronger than strong. Most of it is called strong rigidity, and this is a.
But strong is not stronger than nothing.
Strong is very strong.
Strong rigidity is not stronger than rigidity.
It does not imply okay. Most of strong rigidity does not imply local rigidity. Although in some situation, Nicolas Bergeron and I wrote a paper how to deduce local rigidity from most of rigidity, but you have to work. So here is a sketch proof of this corollary. So let G be, let's say, a Q defined over Q. You can do it in general for any G, but let's in the last 7 minutes let's do it for SL and R. So it's an algebraic group defined over Q, simple algebraic group, and let gamma in G be a lattice. So we already know that up to conjugation, this we saw local rigidity implies that up to conjugation, gamma is contained in G of K where k is a number field. Right? We saw it. So since gamma is finitely generated, we know actually that gamma is contained in a finitely generated subring of k. So what is so in G of, let's say, O k, the ring of integer, but you want to take the inverses of finitely many primes. So I do it fast. So this, for those who study algebraic number theory, this notion should be familiar. This is the ring of integer in K, and this is when I invert finitely many primes. So because gamma is finitely generated, then you have this. Sorry?
So you're almost done.
Yes. So now, look, for any prime, or for any valuation, for any, let's say, finite valuation of k, so if k is q, you have all the periodic valuation. If k is the finite extension of q, you have the extension of the periodic valuation. Look at the map gamma sent to, look at the map gamma inside G of k sent into G of the local field, the corresponding local field, say QP. So whenever if V is not in S, then we know that the image is in G of OKV. And if V is in S, the image is, what can we say about the image? Is bounded. Why is it bounded? Because if it was unbounded, then superrigidity will tell you that you can extend the map to G, but there are no maps from SL and R into totally disconnected groups. So it means that the image is bounded. But if it's bounded, then up to a finite index, if you replace gamma by a finite index subgroup, it actually lays. So replace gamma, take gamma prime inside gamma of finite index, in the notation of Bergeron, we can have that rho, that gamma prime sits inside G of O, the ring of integer of K, for every V. Because S was finite, and in any place, in any place in S, we have to take finite index. Okay. So, up to replacing gamma by a finite index subgroup, we know that gamma prime sit in G SLN of OK, right? So I'm using this lemma from number theory that OK is the intersection of K with all O KV for all V finite valuation. So the rational number whose periodic valuation is 0 for every prime P are exactly the integers. It's non-positive. Is yeah. Non-negative. Yeah, non-negative. So okay, the periodic absolute value is at most 1. Yes. So these are okay. So we know that gamma is here. Now we look at the infinite valuation. So embed this in the product of G of, let's call him R.
Why are you not done?
Yeah, I'm basically done. So I'm basically, I look in the product of KV where V is infinite. So you have finitely many infinite valuation. And I look at the image of gamma in this product. Okay?
This is embedding? This is embedding? Yes.
Yes. So I look at this is a finite product. So each KV is either R or C.
Like you mean SLN?
SLN. G is SLN, but everything I do works for any G.
This is not an SLN OK. Some G OK, or G is a form of SLN or something, right?
No. I didn't change the group. I just changed the valuation. It's the same SLN. Yeah. I do a Galois automorphism for the.
But you had G on the right hand side. It was the fancy G, right?
Yeah, but G is SLN. No, it's all in SLN. You can do it for general G, but all these G's are SLN, and I do the Galois automorphism just for the number field. I don't change the group. Just for simplicity, you can do it for any G, but I take SLN, and I have gamma, and I do Galois automorphism. So I have this. So this is a finite product of SLN-R and SLN-C. And in some of, then you take the Zariski closure of what you get, and then you realize that this is exactly the restriction of scalars. This is the restriction of scalars from Q to K of SLN. And then when you take the Zariski closure and use the fact that the gamma is simple, you see that some of the factor may be compact. But then there could be only one non-compact factor.
SLN-C can be compact? What do you mean by it?
Yeah, now this, let's call it now F. And then you look at, and let's call this group H. And then look at F of gamma, the Zariski closure, inside H. And then it's a semi-simple group. When you check the details, you see that it's exactly the restriction of scalars. This will be the restriction of scalar from Q to K.
The image of F is this, yes?
Sorry?
In the left-hand side.
Yes, the Zariski closure turn out to be the restriction of scalars from Q to K. Okay. Superrigidity tells you that if so this will be a product of simple group. If any factor could be either compact or non-compact, but if it's non-compact by superrigidity, this factor is SLN-R. You can extend it, and since so basically what you get, I'm confused, but basically what you get, you get in this image SLN-R times compact factors.
Theoretically, you can have several copies of SLN-R. That's the claim.
No, I mean it can be like diagonally embedded in several copies. You take the Zariski closure, you will get that there is only one simple factor, which is non-compact. Otherwise, it won't be Zariski dense. And
Project on modulo all the compact.
if you project modulo all the compact, you will get SLN. Yeah, right. That's maybe nicer way to say it. If you, yes.
Can we take 5 more minutes and finish this properly? Shame that.
What was not clear?
We are now proving it's complex.
What? Okay. Questions.
Can you take questions? So
So basically, you have this map into this product. This you agree? And then you take the Zariski closure. And it's okay. Basically, if you want to say it correctly, in the Zariski closure you have a solvable radical. At the end, it turns out to be trivial, but you don't know it, so you have a solvable radical, and you divide by the solvable radical, and then you have a semi-simple group. The semi-simple group has compact factor and non-compact factor. You divide out the compact factor, and you have only non-compact factors. But then, if you look at the map to each of them, by superrigidity, you get that each of them must be a copy of SLNR. If there was more than one copy, then the image could not be Zariski dense. So basically, there is one copy of SLNR, and the rest are compact factors. And and by what Gil described yesterday about restriction of scalars, this is exactly the restriction of scalars, and the SLN OK sits inside. So the SLN OK will sit inside H of Z. So it will, when you do the restriction of scalar, OK goes to Z, and a priori, it's you don't know it's a finite index, but since you know it's a finite volume, then it must be a finite index. Now, I said, I think, all the details, but a bit fast.
Any more questions?
Everything was clear.
Thanks, Ike, again. Just a reminder, there's a session on visualizing arithmetic manifolds. Not arithmetic. Hyperbolic manifolds. So at 8 o'clock, if you're after dinner.
What?
I'm really happy because